after 46 years outside the solar system. Right now, at this very moment as you sit there watching this video, there is a tiny machine, no bigger than a small car, hurtling through the absolute darkness of interstellar space at 17 kilometers per second. It is more than 15 billion miles away from Earth. It is the farthest human-made object in the entire history of our civilization. The temperature around it is negative 270 degrees Celsius, just a few degrees above absolute zero, the coldest anything can possibly get in this universe. There is no light out there, there is no sound. There is nothing but the faintest whisper of hydrogen atoms drifting through the void between the stars. And yet, this little machine, built with technology from the 1970s, with a computer that has less memory than the cheapest calculator you can buy today, is still alive. It is still sending signals back to Earth. Those signals, traveling at the speed of light, the fastest speed possible in the universe, take more than 22 hours to reach us. 22 hours, one way. That means if we send a command to this machine right now, we will not get a response for almost 2 full days. And the signal that arrives here on Earth, after crossing 15 billion miles of empty space, is so unbelievably faint that it is 20 billion times weaker than the power of a single watch battery. And yet, we can hear it. We can decode it. We can understand what it is telling us about the universe beyond our solar system. This machine is called Voyager 1, and its story is, without any exaggeration, the greatest exploration story ever told. But here's the thing that should really blow your mind. Voyager 1 was not alone. It has a twin, Voyager 2. And together, these two spacecraft have done something that no other machine, no other mission, no other human endeavor has ever accomplished. They have visited Jupiter. They have visited Saturn. They have visited Uranus. They have visited Neptune. They have discovered active volcanoes on a world that nobody thought could possibly be geologically alive. They have found evidence of a hidden ocean beneath the frozen surface of a moon that could harbor extraterrestrial life. They have revealed that Saturn's rings, which look so simple and elegant from Earth, are actually made up of thousands upon thousands of individual ringlets, with particles ranging from tiny dust grains to chunks the size of houses. They have discovered new moons, new rings, new magnetic fields, and new phenomena that completely overturned everything we thought we knew about the outer solar system. And then, after all of that, after decades of flying through the cold emptiness of space, they did something that had never been done before, and may not be done again for a very long time. They left the solar system. They crossed the boundary where the sun's influence ends and interstellar space begins. They became the first emissaries of humanity to touch the space between the stars. And what they found out there has surprised, puzzled, and amazed scientists in ways that nobody expected. Now, I want you to think about something for a moment. When Voyager 1 and Voyager 2 were launched in 1977, the world was a very different place. There were no smartphones, there was no internet, there was no GPS, there were no personal computers. People were still using typewriters. The most advanced video game was Pong, a simple white dot bouncing back and forth on a black screen. Disco music was at its peak. Star Wars had just been released in theaters. The Cold War was at its height, with the United States and the Soviet Union pointing thousands of nuclear weapons at each other, capable of destroying the entire planet several times over. And yet, in the midst of all that, a group of scientists and engineers at the Jet Propulsion Laboratory in Pasadena, California, dared to dream of something extraordinary. They dared to send 2 small spacecraft on a journey that would take them to the edge of the solar system and beyond. They dared to include, on each spacecraft, a golden record, a 12-inch gold-plated copper disc containing sounds, music, images, and greetings from Earth. A message in a bottle cast into the cosmic ocean, intended for any intelligent beings who might someday find it drifting through the void between the stars. They dared to imagine a future where humanity would reach beyond its tiny planet and touch the infinite, and they succeeded beyond their wildest dreams. So today, in this video, we are going to take the most incredible journey you have ever experienced. We are going to follow Voyager from the very beginning, from the spark of an idea in the mind of a young mathematician, through the political battles and budget fights that nearly killed the mission, through the nail-biting launch, through the mind-blowing encounters with Jupiter, Saturn, Uranus, and Neptune, through the haunting moment when Voyager turned its camera back toward Earth and took the most famous photograph in human history, through the long, lonely cruise into the darkness, through the historic crossing into interstellar space, through the terrifying technical failures that nearly ended the mission decades after launch, all the way to this very moment, right now, when Voyager is still out there, still transmitting, still fighting against the inevitable decline of its power source, still teaching us things about the universe that we could learn in no other way. We are going to explore every discovery, every mystery, every surprise, every twist and turn of this 46-year odyssey. We are going to go deep into the science, deep into the engineering, deep into the human stories, and deep into the philosophical implications of what it means that we, a species of clever primates on a tiny rock orbiting an ordinary star in an unremarkable corner of an average galaxy, managed to build something that will outlast our planet, our sun, and possibly our entire civilization. This is the story of Voyager, and I promise you by the end of this video you will never look at the night sky the same way again. Let us begin at the very beginning, and the beginning of this story is not at Cape Canaveral, and it is not at the Jet Propulsion Laboratory. The beginning of this story is in the mind of a young aerospace engineer named Gary Flandreau, and the year is 1965. Flandreau was working at JPL on a study of possible future missions to the outer planets, the giant worlds of Jupiter, Saturn, Uranus, and Neptune that orbit in the cold, distant reaches of our solar system. These planets are incredibly far away. Jupiter, the closest of the four, is about 5 times farther from the Sun than Earth. Neptune, the farthest, is 30 times farther. At the speeds that spacecraft typically travel, a direct mission to Neptune would take 30 years or more. That was simply not practical. The spacecraft would break down long before it arrived. The engineers who built it would retire or die before the data came back. It seemed like the outer solar system was simply beyond our reach. But Gary Flandreau discovered something extraordinary. As he plotted the orbits of the 4 giant planets, he realized that in the late 1970s, something incredibly rare was going to happen. All 4 giant planets were going to be lined up on the same side of the Sun, in a configuration that would allow a single spacecraft to visit all 4 of them, one after another, using the gravity of each planet to sling it onward to the next. This technique is called gravity assist, and it is one of the most elegant and beautiful ideas in all of orbital mechanics. Here is how it works. Imagine you are standing next to a moving train, and you throw a ball at the side of the train. The ball bounces off the train and comes back to you faster than you threw it. The ball has stolen a tiny bit of the train's energy, its momentum. The train is so massive that it does not even notice the loss. But the ball has gained a significant boost in speed. Now replace the ball with a spacecraft and the train with a planet, and you have gravity assist. As a spacecraft approaches a planet, it falls into the planet's gravity well, accelerating as it goes. If the trajectory is calculated just right, the spacecraft swings around the planet and is flung outward at a much higher speed than it arrived with, stealing a tiny bit of the planet's orbital energy. The planet, being incomprehensibly more massive than the spacecraft, is completely unaffected. But the spacecraft gets a tremendous boost, allowing it to reach the next planet in a fraction of the time it would otherwise take. And here was the key insight that Gary Flandreau had. The alignment of Jupiter, Saturn, Uranus, and Neptune in the late 1970s would allow a spacecraft to use gravity assist at each planet in turn, hopping from one to the next like a stone skipping across a pond. A spacecraft launched in 1977 could reach Jupiter in about 2 years, use Jupiter's gravity to reach Saturn in another 3 years, use Saturn's gravity to reach Uranus in another 4 years, and use Uranus's gravity to reach Neptune in another 3 years. The entire grand tour of all 4 giant planets could be accomplished in just 12 years. Without gravity assist, the same journey would take 30 years or more. And here is the truly mind-blowing part. This alignment happens only once every 176 years. The last time it happened, Thomas Jefferson was President of the United States. The next time it will happen will be in the year 2153. If NASA missed this window, no one alive in 1977 would live to see the next one. This was, quite literally, a once-in-a-lifetime opportunity. Once in several lifetimes, actually. Flandreau's discovery electrified the space science community. NASA immediately began planning a mission called the Grand Tour, which would send 4 spacecraft to explore all the outer planets. 2 would follow a Jupiter-Saturn-Pluto trajectory, and 2 would follow a Jupiter-Saturn-Uranus-Neptune trajectory. It was an incredibly ambitious plan. But then reality intervened, as it so often does. The Vietnam War was draining the federal budget. NASA's funding was being cut year after year. The Grand Tour program was deemed too expensive, and it was canceled. It looked like the once-in-176-year opportunity would be missed. But the scientists and engineers at JPL did not give up. They went back to the drawing board and came up with a more modest proposal. Instead of 4 spacecraft, they would build just 2. Instead of guaranteeing visits to all 4 planets, they would officially target only Jupiter and Saturn. The missions to Uranus and Neptune would be unofficial bonus objectives, attempted only if the spacecraft survived long enough and if funding continued. The program was renamed from the Grand Tour to Mariner Jupiter-Saturn, and later, just before launch, it was renamed again to something much more poetic, much more fitting for what would become the greatest voyage of exploration in human history. It was renamed Voyager. The 2 Voyager spacecraft were identical twins, and they were masterpieces of engineering. Each one weighed about 825 kilograms, roughly the weight of a small car. Each one carried 11 scientific instruments, including cameras, spectrometers, magnetometers, plasma detectors, cosmic ray detectors, and radio receivers. Each one was equipped with a 3.7-meter high-gain antenna, a large dish-shaped antenna pointed back toward Earth for communication. And each one was powered by something truly remarkable, something that would prove to be the key to the mission's extraordinary longevity. They were powered by radioisotope thermoelectric generators, or RTGs. An RTG is essentially a nuclear battery. It contains a quantity of plutonium-238, a radioactive isotope that produces heat as it decays. That heat is converted into electricity by thermocouples, devices that generate an electric current when one side is hotter than the other. RTGs have no moving parts, nothing to break down, nothing to wear out. They just sit there and generate electricity, year after year after year, as the plutonium slowly decays. At launch, each Voyager's RTGs produced about 470 watts of electrical power, roughly enough to power a few household light bulbs. That might not sound like much, but it was enough to run all of Voyager's instruments and systems. And the beauty of it was that it would keep producing power for decades, slowly declining as the plutonium decayed, but never completely stopping. This was crucial, because Voyager was heading into the outer solar system, where sunlight is so faint that solar panels would be useless. Beyond Jupiter, there simply is not enough sunlight to power a spacecraft. Without the RTGs, the Voyager mission would have been impossible. Now, here is a detail that I find absolutely incredible, and it tells you something about the era in which Voyager was built. The onboard computer of each Voyager spacecraft has a total memory capacity of 69.63 kilobytes. Let me put that in perspective for you. The photo you took of your lunch today and posted on social media is probably about 5 megabytes. That is more than 70 times the entire memory of the Voyager computer. The phone in your pocket right now has roughly 1,000,000 times more computing power than the Voyager spacecraft. A modern digital watch has more memory. And yet, this tiny primitive computer has successfully navigated Voyager across billions of miles, managed thousands of scientific observations, processed and transmitted countless images and data sets, and kept the spacecraft alive and functioning for more than 46 years. It is a testament to the brilliance of the engineers who designed it, and to a fundamental truth about engineering that we sometimes forget in our age of planned obsolescence and annual upgrades. Simplicity and robustness will always outlast complexity and raw power. Voyager was built to last, and it has. The launch of the Voyager spacecraft is a story that contains a delightful irony. Voyager 2 was launched first, on August 20th, 1977, aboard a Titan IIIe Centaur rocket from Cape Canaveral, Florida. Voyager 1 was launched 16 days later, on September 5th, 1977, aboard an identical rocket from the same launch pad. So why is Voyager 1 called 1 if it launched second? The answer is simple and elegant. Voyager 1 was placed on a faster trajectory, a more direct path that would get it to Jupiter and Saturn sooner than Voyager 2, even though it left Earth later. By the time both spacecraft reached Jupiter, Voyager 1 was in the lead, and it has been in the lead ever since. Voyager 1 arrived at Jupiter first, arrived at Saturn first, and was the first to leave the solar system, so it earned the name Voyager 1, not by launching first, but by arriving first. The launch itself was a nerve-wracking experience for everyone involved. Remember, this was 1977. There were no backup spacecraft waiting in the wings. If the rocket exploded on the launch pad, or if the spacecraft failed during its first few days in space, that was it. The mission was over. The once-in-176-year opportunity would be at least half wasted. And indeed, things did not go entirely smoothly. Voyager 2, launched first, experienced a serious problem almost immediately. About a minute into the flight, the rocket began to veer off course. The guidance system detected the error and corrected it, but the correction was so violent that it nearly tore the spacecraft apart. Then, after Voyager 2 separated from the rocket and began its journey to Jupiter, engineers discovered that its primary radio receiver had failed. The backup receiver worked, but it had a flaw. It could not automatically adjust for the Doppler shift caused by the spacecraft's motion relative to Earth. This meant that for the entire rest of the mission, more than 46 years and counting, every command sent to Voyager 2 had to have its frequency manually adjusted by engineers on the ground to compensate for the spacecraft's motion. One small error in this adjustment, and Voyager 2 would not hear the command. This was a significant handicap, and it would cause problems decades later, as we will see. But for now, both spacecraft were on their way, racing outward from the Sun toward their first target, the king of the planets. Jupiter. Jupiter is, in a word, enormous. It is the largest planet in our solar system by a wide margin. Its diameter is 11 times that of Earth. Its volume could contain more than 1,300 Earths. Its mass is more than twice that of all the other planets in the solar system combined. If Jupiter had been just a little bit more massive, perhaps 80 times more massive, it would have ignited nuclear fusion in its core and become a star. We would be living in a binary star system. But Jupiter fell just short of that threshold, and so it became something else. A gas giant, a massive ball of hydrogen and helium with no solid surface, just an atmosphere that gets denser and denser as you go deeper, eventually transitioning into liquid hydrogen, then metallic hydrogen, and finally, perhaps, a small rocky core at the very center, crushed under pressures millions of times greater than the pressure at the bottom of Earth's deepest ocean. Before Voyager, we knew relatively little about Jupiter. We knew it was big. We knew it had colorful bands of clouds. We knew about the Great Red Spot, a massive storm that had been observed by astronomers through telescopes for more than 300 years. We knew Jupiter had 4 large moons, the Galilean moons discovered by Galileo in 1610, named Io, Europa, Ganymede, and Callisto, but we had never seen Jupiter up close. We had never seen its moons as anything more than tiny points of light. We had no idea what wonders and horrors awaited us there. Voyager 1 arrived at Jupiter on March 5, 1979, after a journey of about 18 months. Voyager 2 arrived on July 9th of the same year, and what they found there changed everything we thought we knew about the outer solar system. Let us start with the planet itself. The first thing that struck the Voyager scientists as the images came in was the incredible beauty and complexity of Jupiter's atmosphere. From Earth, Jupiter's cloud bands look relatively smooth and orderly, alternating stripes of light and dark encircling the planet. But from up close, Voyager revealed a world of staggering atmospheric violence and beauty. The cloud bands were not smooth at all. They were turbulent, chaotic, swirling masses of gas, filled with eddies and vortices and cyclones and anticyclones that interacted with each other in complex, constantly changing patterns. The colors were extraordinary, shades of orange, red, brown, yellow, and white, created by trace chemicals in Jupiter's atmosphere, ammonia, ammonium hydrosulfide, water, and various organic compounds, all drawn up from the depths by powerful convection currents and altered by the fierce ultraviolet radiation from the sun. And then there was the Great Red Spot. Astronomers had been observing this feature through telescopes for centuries, but no one had ever seen it like this. Voyager's cameras revealed that the Great Red Spot is a colossal anticyclonic storm, a high-pressure system that rotates counterclockwise in Jupiter's southern hemisphere. It is so large that 2 to 3 Earths could fit inside it. Its wind speeds reach 430 kilometers per hour at the edges. Its cloud tops rise 8 kilometers above the surrounding atmosphere. It is, quite possibly, the longest-lived storm in the known universe, having raged continuously for at least 350 years, and possibly much longer. Voyager showed that the Great Red Spot is not a static feature but a dynamic, living thing. It absorbs smaller storms that drift too close, consuming them and growing temporarily larger before settling back to its normal size. Its color changes over time, sometimes deepening to a vivid brick red, sometimes fading to a pale salmon pink. The exact chemical that gives it its red color is still debated to this day, though most scientists believe it is related to complex organic molecules created by ultraviolet radiation, breaking apart chemicals that are drawn up from deep in the atmosphere. If this storm existed on Earth, it would be an unimaginable catastrophe. It would engulf entire continents. Its winds would flatten every structure ever built by humans. It would be, quite literally, an apocalypse. On Jupiter, it is just one more feature in a world of perpetual atmospheric chaos. But as incredible as Jupiter itself was, it was the moons that truly stole the show. And of all the discoveries that Voyager made at Jupiter, and indeed of all the discoveries that Voyager made during its entire 46-year mission, perhaps the most shocking, the most unexpected, the most paradigm-shattering was what it found on the innermost of the 4 Galilean moons, a world called Io. Before Voyager, scientists expected Io to be a dead, cratered world, not unlike our own moon. There was no reason to think otherwise. Io is small, only slightly larger than Earth's moon. Small bodies cool quickly and lose their internal heat, which means they lose the geological activity that heat drives. Our moon has been essentially dead for billions of years. Mars, which is much larger than Io, has been mostly dead for billions of years. Io, being smaller than either of them, should have been dead for even longer. It should have been a cold, quiet, cratered ball of rock. It was not. The discovery happened almost by accident. On March 9, 1979, a few days after Voyager 1's closest approach to Jupiter, a young navigation engineer named Linda Morabito was processing images of Io that were being used not for science, but for navigation, to help determine the spacecraft's exact position. She noticed something strange on the edge of Io's disk, a bright, crescent-shaped feature that did not match any surface feature. At first, she thought it might be another moon behind Io, or perhaps a processing artifact. But as she examined it more closely, she realized what it was. It was a massive plume of material, 300 kilometers high, erupting from the surface of Io. It was a volcanic eruption, an active, ongoing volcanic eruption on another world. This was the first time active volcanism had ever been observed anywhere in the solar system other than Earth. And it was just the beginning. As more images were processed, and as Voyager 2 arrived at Jupiter 4 months later and flew even closer to Io, the full picture emerged, and it was astonishing. Io was not just volcanically active, it was the most volcanically active body in the entire solar system, by far. Not even close. Voyager observed at least 9 active volcanic eruptions during its flybys, and subsequent observations have revealed that Io has more than 400 active volcanoes. Its surface is a hellscape of sulfur and silicate lava, with volcanic plumes reaching 300 kilometers into space, with lava lakes and lava flows stretching hundreds of kilometers across the surface, with temperatures at some eruption sites exceeding 1700 degrees Celsius, hotter than anything found on the surface of Earth. The surface of Io is so constantly renewed by volcanic activity that there are virtually no impact craters on it at all. On every other solid body in the solar system, impact craters from asteroids and comets are visible, some of them billions of years old. But on Io, the surface is so young, so constantly resurfaced by lava, that any crater that forms is quickly buried and erased. The entire surface of Io is replaced every million years or so. In geological terms, that is the blink of an eye. But what could possibly be causing all this activity? Io is tiny. It should have lost its internal heat long ago. The answer, which had actually been predicted in a theoretical paper published just weeks before Voyager's arrival by the scientists Stan Peele, Patrick Casson, and Ray Reynolds, is something called tidal heating. Io orbits very close to Jupiter, the most massive planet in the solar system. And Io is locked in a gravitational dance with 2 other large moons, Europa and Ganymede, in what is called a Laplace resonance. For every 4 orbits Io makes around Jupiter, Europa makes exactly 2, and Ganymede makes exactly 1. This resonance keeps Io's orbit slightly elliptical, which means that Io's distance from Jupiter varies as it goes around its orbit. And because Jupiter's gravity is so immense, this variation in distance causes enormous tidal forces on Io, literally stretching and squeezing the Moon as it orbits. This is not the gentle tidal effect that the Moon has on Earth's oceans. This is a violent, relentless knotting of Io's entire interior, generating enormous amounts of heat through friction. This heat melts rock inside Io, creating the magma that feeds its hundreds of volcanoes. In effect, Jupiter is cooking Io alive, has been cooking it for billions of years, and will continue to cook it for billions more. But the revolution that Io represented went far beyond one moon. Before Voyager reached Jupiter, the prevailing view among planetary scientists was that moons were boring. They were dead rocks, they were cratered, cold, and geologically inactive. The only interesting worlds in the solar system were the planets. Io shattered this view completely. Io showed that moons could be just as dynamic, just as active, just as geologically alive as any planet. And this paradigm shift opened the door to what many scientists consider to be the single most important discovery in the entire history of planetary exploration: Europa. Europa is the second of the 4 Galilean moons, orbiting slightly farther from Jupiter than Io. It is roughly the size of Earth's moon. And when Voyager's cameras turned their attention to Europa, they revealed a world unlike anything anyone had ever seen. Europa's surface is covered in water ice, but it is not the scarred, cratered ice you might expect. Instead, Europa has the smoothest surface of any solid body in the solar system. It is almost perfectly flat, with very few impact craters, just like Io. But where Io's surface is renewed by volcanic lava, Europa's surface is renewed by something else entirely. The surface of Europa is crisscrossed by an intricate network of lines, ridges, and cracks, stretching for thousands of kilometers across the moon's face. These features look, more than anything else, like the cracks that form on the surface of sea ice on Earth when it is broken apart and then refreezes. The implication was staggering and immediate. These cracks suggested that Europa's ice shell is not sitting on solid rock. It is floating on liquid water. Beneath the frozen surface of Europa, there appears to be a vast global ocean of liquid water. And the same mechanism that heats Io, tidal heating from Jupiter's gravity, is responsible for keeping this ocean liquid. Europa is in the same Laplace resonance with Io and Ganymede. It experiences the same tidal forces. But because Europa is farther from Jupiter, the heating is less intense. Instead of melting rock, it melts ice. Instead of creating volcanoes, it creates an ocean. How big is this ocean? Current estimates suggest that Europa's ice shell is between 15 and 25 kilometers thick. Below that, the ocean may be 60 to 150 kilometers deep. If these estimates are correct, Europa has more liquid water than all of the oceans on Earth combined. More than twice as much, actually. And where there is liquid water, there is the possibility of life. On Earth, life exists everywhere there is liquid water, from boiling hot springs to freezing Antarctic lakes, from the deepest ocean trenches to tiny pores in underground rocks. If Europa has a global ocean of liquid water, kept warm by tidal heating, with a rocky seafloor where chemical reactions could provide energy, then it has all the basic ingredients for life. Not human life, of course, not plants or animals, but microbial life, bacteria, simple organisms, the kind of life that existed on Earth for the first 3 billion years of its history, before complex multicellular organisms evolved. This is not science fiction. This is mainstream science. Europa is considered by many astrobiologists to be the single most promising place in the solar system to search for extraterrestrial life. NASA is currently building a mission called Europa Clipper, specifically to study Europa's ocean and assess its habitability. And the trail that led to Europa Clipper started right here with Voyager in 1979. Think about that for a moment. A spacecraft built in the 1970s with a computer that has less memory than a birthday card may have pointed us toward the discovery of life beyond Earth. If life is eventually found on Europa, and many scientists believe it will be, the implications will be profound. It will mean that life is not a rare accident that happened only once on our planet. It will mean that life is a common phenomenon, arising wherever conditions are right. It will mean that the universe is likely teeming with life. And it all traces back to those cracked ice images from Voyager. But Jupiter had more wonders to reveal. Ganymede, the third Galilean moon, turned out to be the largest moon in the entire solar system, larger even than the planet Mercury. It is the only moon known to have its own internally generated magnetic field, a miniature version of Earth's magnetic field, suggesting that it has a liquid iron core, just like Earth. Its surface is a fascinating patchwork of two different types of terrain: old, dark, heavily cratered regions, and younger, lighter, grooved regions where the surface has been tectonically reshaped. Ganymede, too, may have a subsurface ocean, sandwiched between layers of ice deep within the moon. Callisto, the outermost Galilean moon, is the most heavily cratered body in the solar system. Its surface has been pummeled by impacts for over 4 billion years, and because Callisto has no significant geological activity, every scar remains. The most prominent feature is the Valhalla Impact Basin, a multi-ringed structure 3,800 kilometers across, the result of a colossal impact that shook the entire moon. And even Callisto, seemingly the most boring of the 4 Galilean moons, may harbor surprises. There is evidence suggesting that it, too, may have a subsurface ocean, far beneath its ancient cratered surface. And as if all of this were not enough, Voyager made yet another unexpected discovery at Jupiter. It found that Jupiter has rings. Nobody expected this. Rings were thought to be a feature unique to Saturn. But Voyager 1's cameras, looking back at Jupiter with the sun behind it, detected a thin, faint ring system encircling the planet. Unlike Saturn's bright, icy rings, Jupiter's rings are made of tiny dust particles, probably knocked off the surfaces of small inner moons by micrometeorite impacts. They are so faint and tenuous that they are invisible from Earth with all but the most powerful telescopes. Without Voyager, we might not have discovered them for decades. Voyager also gave us our first detailed look at Jupiter's magnetosphere, the region of space dominated by the planet's magnetic field. Jupiter has the strongest magnetic field of any planet in the solar system, about 20,000 times stronger than Earth's. This powerful magnetic field traps enormous quantities of charged particles, primarily electrons and protons, creating radiation belts of extraordinary intensity. The radiation environment around Jupiter is so fierce that it would be lethal to an unprotected human in minutes. Even Voyager, shielded as it was by its design, suffered some radiation damage to its electronics during its closest approach. Voyager also observed spectacular auroras at Jupiter's poles, similar to Earth's northern and southern lights, but on a vastly larger scale, powered by the interaction between Jupiter's magnetosphere and the solar wind. Jupiter was a triumph. It exceeded every expectation, but the journey was far from over. Using Jupiter's gravity as a slingshot, both Voyagers were flung outward toward their next destination, the most beautiful planet in the solar system, Saturn. If Jupiter is the king of the planets, then Saturn is the jewel. Even through a small telescope from Earth, Saturn is breathtaking, a pale gold globe encircled by those magnificent rings. No other sight in the sky compares to it. Saturn has inspired wonder and fascination for as long as humans have looked up at the night sky. Galileo was the first to observe its rings through a telescope in 1610, but his telescope was too primitive to resolve them clearly. He thought Saturn had ears, or was accompanied by two large moons that never moved. It was not until 1655 that Christian Huygens, using a better telescope, correctly identified the rings as a flat disk encircling the planet. And for more than 300 years after that, Saturn's rings remained one of the most beautiful and mysterious features in all of astronomy. Voyager 1 arrived at Saturn on November 12, 1980. Voyager 2 arrived on August 26, 1981, and what they found there was even more spectacular than anyone had imagined. From Earth, Saturn's rings appear to be composed of a few broad, distinct bands separated by dark gaps. The most prominent gap, the Cassini division, is easily visible through a modest telescope. It seemed like a relatively simple structure. Voyager proved otherwise. As the spacecraft drew closer and the resolution of its images improved, the few broad rings dissolved into hundreds of ringlets. And as it got even closer, those hundreds became thousands. Saturn's ring system turned out to be of staggering complexity, composed of literally thousands upon thousands of individual ringlets, some sharp and well-defined, others diffuse and blending into their neighbors, arranged in an intricate pattern that no one had anticipated. The rings are made primarily of particles of water ice, ranging in size from tiny grains smaller than a grain of sand to enormous chunks the size of a house or even larger. Despite their enormous extent, spanning more than 280,000 kilometers from inner to outer edge, a distance nearly equal to the distance from Earth to the Moon, the rings are incredibly thin. Most of the ring material is contained within a layer only about 10 to 30 meters thick. To put that in perspective, if you shrank Saturn's rings down to the diameter of a football field, they would be thinner than a sheet of paper. They are, proportionally, the thinnest structure in the known universe that maintains its coherent shape. Voyager discovered numerous new features within the rings that had never been seen before. It found the Encke gap, a narrow gap in the outer A ring, and within it, a tiny moon called Pan, only 28 kilometers across, whose gravity sweeps the gap clear of ring particles. This was the first example of what scientists call a shepherd moon, a moon whose gravitational influence shapes and maintains a ring feature. Voyager also found the F ring, a narrow, twisted ring just outside the main ring system, flanked by two shepherd moons, Prometheus and Pandora, whose gravity confines the ring particles into their narrow band. The F ring itself displayed bizarre structures, braids, kinks, and clumps, caused by the complex gravitational interactions between the ring particles and the shepherd moons. One of the most puzzling discoveries in the rings was the spokes. These were dark, radial markings that appeared in the B ring, the brightest and densest part of the ring system. They extended radially outward from near the inner edge of the B ring, like the spokes of a bicycle wheel. This was deeply puzzling because ring particles at different distances from Saturn orbit at different speeds. Any radial feature should be quickly sheared apart by this differential rotation, and yet the spokes persisted, sometimes for hours, before gradually dissolving. They appeared to rotate with Saturn's magnetic field rather than with the ring particles, suggesting that they were somehow being influenced by electromagnetic forces. The leading theory is that the spokes are composed of tiny, electrically charged dust particles that are levitated above the ring plane by Saturn's magnetic field. But the exact mechanism is still debated. Even decades later, after the Cassini mission spent 13 years studying Saturn, the spokes remain not fully understood. They are one of those beautiful mysteries that remind us how much we still have to learn. But Saturn, like Jupiter, is more than just a planet. It is a system, a miniature solar system in its own right, with a retinue of moons that range from tiny shepherds of the rings to worlds large enough to have their own atmospheres and geological activity. And of all Saturn's moons, the one that most captured the imagination of scientists was the giant moon Titan. Titan is the largest moon of Saturn and the second largest moon in the solar system after Jupiter's Ganymede. It is larger than the planet Mercury. But what makes Titan truly unique, what sets it apart from every other moon in the entire solar system, is that it has a thick atmosphere. Not just a wisp of gas clinging to its surface, but a substantial, dense atmosphere, thicker than Earth's. Titan's atmospheric pressure at the surface is about 1.5 times that of Earth. If you stood on the surface of Titan, you would feel about 50% more atmospheric pressure pushing on you than you feel right now. The atmosphere is composed primarily of nitrogen, about 95%, with the remaining 5% mostly methane and trace amounts of other organic compounds. Nitrogen is also the primary component of Earth's atmosphere, making up about 78%. This similarity is tantalizing and suggestive. Earth's early atmosphere, before life transformed it by adding oxygen, may have been somewhat similar to Titan's current atmosphere. But here's the frustrating thing. Titan's atmosphere is shrouded in a thick orange haze, a smog of complex organic molecules called tholins, created by ultraviolet radiation from the sun, breaking apart methane and nitrogen in the upper atmosphere, and allowing the fragments to recombine into ever larger, more complex molecules. This haze is so thick that Voyager's cameras could not see through it to the surface below. Voyager gave us incredible data about Titan's atmosphere, its composition, its temperature profile, its structure, but it could not tell us what lay beneath. The surface of Titan remained hidden, a tantalizing mystery. What we now know, thanks to the Cassini-Huygens mission that arrived at Saturn in 2004, 23 years after Voyager, is that Titan's surface is one of the most extraordinary places in the solar system. It has lakes and seas, not of water, but of liquid methane and ethane. It has rain, not water rain, but methane rain, falling from methane clouds through a methane-saturated atmosphere onto a surface carved by methane rivers into methane lakes. It has dunes, mountains, and canyons. It has a complete, Earth-like hydrological cycle with evaporation, cloud formation, precipitation, and surface flow, but all based on hydrocarbons instead of water. In many ways, Titan is the most Earth-like world in the solar system, not because of its temperature, which is a frigid -179 degrees Celsius, but because of its complex atmospheric chemistry, its liquid cycle, and its diverse surface geology. Some scientists have speculated that exotic forms of life might be possible on Titan, life that uses liquid methane as a solvent instead of water. This is highly speculative, but the fact that we can even seriously discuss it is a testament to just how remarkable Titan is. And it was Voyager that first revealed Titan's thick atmosphere, first measured its composition, first showed us that this was a world worth returning to. The frustration of not being able to see through the haze directly motivated the Cassini-Huygens mission, which included a probe, Huygens, that descended through Titan's atmosphere and landed on its surface on January 14, 2005, the most distant landing ever achieved by a human-made spacecraft. And now NASA is building yet another mission to Titan, called Dragonfly, a rotorcraft lander that will fly through Titan's thick atmosphere, hopping from location to location, exploring the surface and searching for signs of prebiotic chemistry or even life. The chain of discovery that started with Voyager continues to this day. Voyager also gave us intriguing glimpses of other Saturnian moons. Enceladus, a small moon only 500 kilometers in diameter, displayed a remarkably bright white surface, the most reflective surface of any body in the solar system. Voyager saw hints that Enceladus might be geologically active, and decades later, the Cassini mission confirmed this in spectacular fashion, discovering enormous geysers of water vapor and ice particles erupting from fractures near Enceladus's south pole. Like Europa, Enceladus has a subsurface ocean of liquid water, heated by tidal forces, and like Europa, it is considered a prime candidate for extraterrestrial life. Mimas, another small moon, displayed a giant impact crater called Herschel that made it look uncannily like the Death Star from Star Wars, which had been released just 3 years before Voyager arrived. Iapetus displayed a bizarre two-toned surface, one hemisphere bright and the other dark as coal, a mystery that was not fully explained until Cassini arrived decades later. Hyperion, a small, irregularly shaped moon, looked like a sponge, covered in deep, sharp-edged craters with dark material at their bottoms. Now, at Saturn, something happened that would have profound consequences for the rest of the Voyager mission. Voyager 1 had been assigned to make a close flyby of Titan, passing within 4,000 kilometers of the moon's surface to get the best possible data on its atmosphere. But the trajectory required for this close Titan flyby meant that after Saturn, Voyager 1 would be deflected sharply upward, out of the plane of the solar system. It would not be able to continue on to Uranus and Neptune. This was a deliberate choice. NASA decided that the scientific value of a close Titan flyby was greater than the value of sending Voyager 1 to the outer planets. Titan's thick atmosphere was simply too important to pass up. But it meant that the responsibility of visiting Uranus and Neptune fell entirely on Voyager 2. One spacecraft, no backup. If anything went wrong with Voyager 2, those two planets would remain unexplored, possibly for decades. The pressure on the Voyager 2 team was immense. And so, as Voyager 1 arced away from Saturn and began its long climb out of the ecliptic plane, heading for the stars, Voyager 2 pressed on alone, deeper into the outer solar system, toward a planet that no spacecraft had ever visited. Before we continue on that journey, I want to ask you something. Are you enjoying this? Because we are only about a third of the way through, and the best is yet to come. If you are finding this fascinating, if you are learning things you never knew, if this journey through the solar system is capturing your imagination, then do me a favor. Hit that like button right now. It really does help, more than you might think. And if you are not already subscribed, go ahead and subscribe and hit the notification bell so you do not miss the next deep dive like this. And in the comments, tell me this. So far, which discovery has blown your mind the most? Is it Io's volcanoes, Europa's ocean, Saturn's impossibly thin rings? Let me know. And now, let us continue our journey into the unknown. Uranus. For 4.5 years after leaving Saturn, Voyager 2 flew alone through the emptiness of the outer solar system. There was nothing to see, nothing to photograph, nothing to study. Just empty space, getting colder and darker with every passing day as the sun shrank to a bright but increasingly distant point of light. The Voyager team used this time to prepare for the Uranus encounter, reprogramming the spacecraft's ancient computers to account for the challenges that lay ahead. Uranus was much farther from the sun than Saturn, which meant much less light, which meant longer exposure times for the cameras, which meant a greater risk of blurred images as the spacecraft sped past. The team developed new image compression algorithms that could be uploaded to Voyager 2's computers, allowing it to transmit more data with its limited power. They also developed a technique called image motion compensation, in which the entire spacecraft would slowly rotate during each camera exposure to compensate for its own motion, keeping the image sharp. These software innovations, uploaded to a spacecraft billions of miles away, were remarkable feats of engineering. On January 24, 1986, Voyager 2 arrived at Uranus. It was the first, and as of today, the only spacecraft ever to visit this planet. No other spacecraft has been to Uranus since. No other spacecraft is currently on its way to Uranus. Every single thing we know about Uranus from close-up, every detailed image, every magnetic field measurement, every atmospheric observation comes from this one flyby by one spacecraft on one day in 1986. Let that sink in for a moment. We have sent multiple orbiters to Mars. We have sent multiple missions to Jupiter and Saturn. We have sent a spacecraft to Pluto. But Uranus has been visited exactly once, for a few hours, nearly 40 years ago. It is one of the great gaps in our exploration of the solar system, and it is a gap that many planetary scientists are desperate to fill. The most recent Planetary Science Decadal Survey, the document that sets priorities for NASA's planetary exploration program, identified a Uranus orbiter mission as its top priority for the coming decade. But such a mission, even if approved immediately, would not arrive at Uranus until the late 2030s or 2040s. Voyager's data remains our best and only close-up look at this strange world. And strange is the right word. Uranus is deeply, profoundly strange. The most obvious oddity is its axial tilt. Every planet in the solar system rotates on an axis that is tilted relative to its orbital plane. Earth's axial tilt is about 23.5 degrees, which is what gives us our seasons. Most planets have tilts in a similar range, but Uranus's axial tilt is 98 degrees. It is tilted so far over that it is essentially rolling on its side as it orbits the Sun. Its poles take turns pointing almost directly at the Sun. During a Uranian summer, the North Pole faces the Sun for 21 years straight, while the South Pole is in complete darkness. Then, gradually, the planet's orientation shifts until the South Pole faces the Sun for 21 years, while the North Pole is dark. Spring and autumn, when the equator faces the Sun, last about 21 years each as well. A full year on Uranus, one complete orbit around the Sun, takes 84 Earth years. And for roughly half that time, one pole or the other is in continuous sunlight, while the opposite pole is in continuous darkness. Imagine living on a world where the sun rises, and then does not set for 21 years. And then it sets, and does not rise again for another 21 years. Uranus has the most extreme seasons of any planet in the solar system, all because of that bizarre axial tilt. What caused it? The leading theory is that early in the history of the solar system, during the chaotic period when planets were still forming and giant impacts were common, Uranus was struck by an Earth-sized object that knocked it onto its side. This is the same type of event that is thought to have created Earth's moon, when a Mars-sized object struck the early Earth and blasted enough material into orbit to coalesce into the moon. But in Earth's case, the impact tilted the planet by only about 23 degrees. In Uranus's case, the impact was apparently more severe, or struck at a different angle, tilting the planet by a full 98 degrees. Some models suggest it may have taken not one, but two large impacts to achieve the current tilt. When Voyager 2 arrived at Uranus, scientists were eager to see what the atmosphere of this strange, sideways world looked like. Would the extreme seasonal heating create dramatic weather patterns? Would there be giant storms and colorful cloud bands like Jupiter and Saturn? The answer was, to everyone's initial disappointment, no. Uranus appeared almost featureless. Its atmosphere was a uniform pale blue-green, with barely any visible cloud features. It was, to use the word the scientists themselves used at the time, boring. After the visual feasts of Jupiter and Saturn, with their vivid colors and dramatic storms, Uranus seemed like an anticlimactic letdown. But this apparent blandness was itself a mystery, and a deep one. Why was Uranus so featureless? The answer seems to lie in another of Uranus's oddities. Unlike Jupiter, Saturn, and Neptune, Uranus radiates virtually no excess internal heat. Most of the giant planets radiate significantly more energy than they receive from the Sun, indicating that they have substantial reservoirs of internal heat left over from their formation. Jupiter radiates about twice as much energy as it receives from the Sun. Saturn radiates about 2.5 times as much. Even Neptune, as we will see, radiates more than twice as much. But Uranus radiates almost exactly as much as it receives, and no more. It appears to have very little internal heat. Without this internal heat to drive convection and stir up the atmosphere, Uranus's atmosphere is relatively calm and stratified, producing the bland appearance that Voyager observed. But why Uranus lacks internal heat when the other giant planets do not, is a question that has no definitive answer. It may be related to the same giant impact that knocked the planet on its side, perhaps disrupting the normal process by which heat from the interior is transported to the surface. Or it may be related to the planet's internal structure, which we understand only poorly. Whatever the reason, Uranus's missing internal heat remains one of the great unsolved mysteries of planetary science. The blue-green color of Uranus is easier to explain. Uranus's atmosphere is composed primarily of hydrogen and helium, like Jupiter and Saturn, but it also contains a small but significant amount of methane. Methane absorbs red light very efficiently. When sunlight enters Uranus's atmosphere, the methane absorbs the red end of the spectrum and allows the blue and green wavelengths to be reflected back into space, giving the planet its distinctive color. Voyager 2's measurements of Uranus's magnetic field produced one of the biggest surprises of the entire encounter. Magnetic fields in the solar system are generally aligned roughly with a planet's rotation axis. Earth's magnetic field is tilted about 11 degrees from its rotation axis, which is why magnetic north is not exactly at the geographic North Pole, but close to it. Jupiter and Saturn have magnetic fields that are similarly well aligned with their rotation axis. But Uranus's magnetic field is tilted a staggering 59 degrees from its rotation axis. And not only is it tilted, it is also offset from the center of the planet by about 1/3 of the planet's radius. To give you an analogy, imagine if Earth's magnetic field emerged not from near the North Pole, but from somewhere around Tokyo, and was centered not on the middle of the Earth, but on a point several thousand kilometers off to one side. It would be bizarre. It would be unprecedented. And yet, that is exactly what Voyager found at Uranus. This weird magnetic field creates a truly bizarre magnetosphere. On most planets, the magnetosphere is shaped like a teardrop, compressed on the side facing the sun by the solar wind, and stretched out into a long tail on the opposite side, with the magnetic poles near the geographic poles. But because Uranus's magnetic axis is so tilted, and because Uranus itself is tilted on its side, the magnetosphere wobbles wildly as the planet rotates, sometimes pointing toward the sun, sometimes pointing away, creating a corkscrewing, twisting configuration that is unlike anything else in the solar system. The cause of this bizarre magnetic field is thought to be related to Uranus's internal structure. Unlike Jupiter and Saturn, where the magnetic field is generated deep in the core by convecting metallic hydrogen, Uranus's magnetic field may be generated in a relatively shallow shell of electrically conductive water, ammonia, and methane ices at an intermediate depth within the planet. This off-center, off-axis generation produces the weird, tilted, offset field that Voyager observed. Voyager 2 also studied Uranus's ring system. Uranus's rings had been discovered from Earth in 1977, just a few months before Voyager 2's launch, when astronomers observed a star pass behind Uranus and noticed that the star's light dimmed briefly several times before and after it was blocked by the planet itself, indicating the presence of narrow rings. Voyager confirmed and detailed these rings, discovering 11 in total. Unlike Saturn's bright, icy rings, Uranus's rings are extremely dark, among the darkest objects in the solar system. They are composed of particles that are as black as charcoal, possibly made of darkened organic material or processed ice. They are also very narrow, most just a few kilometers wide, and separated by broad empty spaces. Uranus's ring system could not be more different from Saturn's. And then there were the moons. Voyager 2 discovered 10 previously unknown moons of Uranus, bringing the total known at the time from 5 to 15. But the star of the show, the moon that captured everyone's imagination, was Miranda. Miranda is small, only about 470 kilometers in diameter. Before Voyager arrived, it was expected to be a dull, heavily cratered ball of ice and rock, too small to have any interesting geology. But when Voyager 2's images came back, scientists were stunned. Miranda's surface was a chaotic patchwork of different terrains that looked like they had been assembled from pieces of different worlds. There were old, heavily cratered regions, as expected. But interspersed with these were bizarre features called coronae, large, roughly rectangular regions of grooved and ridged terrain that looked completely different from their surroundings. One of these corona, called Inverness corona, features a chevron-shaped pattern of bright and dark ridges that earned it the nickname the chevron. Another, Arden corona, displays a racetrack-like pattern of concentric ridges and grooves. And then there is Verona Rupes. Verona Rupes is a cliff face on Miranda that is approximately 20 kilometers high, making it the tallest known cliff in the entire solar system. 20 kilometers. If you stood at the top and jumped off, it would take you about 12 minutes to reach the bottom, falling in the weak gravity of this tiny moon. You would have time to contemplate your life choices quite thoroughly before impact. What created Miranda's bizarre surface? One early theory suggested that Miranda had been shattered by a massive impact and then reassembled by gravity, with the different types of terrain representing pieces of the original interior and surface all jumbled together. This Humpty Dumpty theory was appealing in its simplicity, but more recent analysis suggests that the coronae were formed by internal geological processes, upwelling of warm ice from the interior, driven by tidal heating similar to what occurs on Io and Europa. Miranda may have experienced more tidal heating in the past than it does today, if it was previously in an orbital resonance with other moons that has since been disrupted. The other major moons of Uranus, Ario, Umbriel, Titania, and Oberon, each revealed their own unique characteristics. Ariel displayed a relatively young surface with extensive systems of grabens, fault valleys formed by extensional tectonics. Umbriel was dark and ancient, heavily cratered, with a mysterious bright ring feature on its surface called Wunda that has never been satisfactorily explained. Titania, the largest of Uranus's moons, displayed enormous canyon systems stretching across its surface, suggesting that the moon expanded at some point in its history, cracking its surface. Oberon, the outermost major moon, was heavily cratered and showed signs of past cryovolcanism, with dark material on the floors of some craters that may have been extruded from the interior. Uranus was a success. Despite the initial disappointment of the bland atmosphere, Voyager 2 had revealed an entire system of wonders: a tilted world with a bizarre magnetic field, dark, narrow rings, a patchwork moon with the solar system's tallest cliff, and a host of geological surprises. But the journey was not over. The best, in many ways, was yet to come. Voyager 2 used Uranus's gravity to sling itself even farther outward, toward the last port of call on its grand tour, the most distant planet in the solar system, Neptune. The journey from Uranus to Neptune took 3.5 years. During that time, Voyager 2 crossed 2 billion kilometers of empty space, plunging ever deeper into the cold, dark outer reaches of the solar system. Neptune orbits the Sun at an average distance of 4.5 billion kilometers, 30 times farther from the Sun than Earth. At that distance, sunlight is 900 times fainter than it is at Earth. The Sun itself, seen from Neptune, would appear as just a very bright star, casting a dim, twilight illumination on the planet and its moons. Voyager 2's cameras, designed for the much brighter conditions at Jupiter and Saturn, would need exposure times of up to 15 seconds to capture usable images at Neptune, an eternity for a spacecraft hurtling past at 27 kilometers per second. The Voyager team once again pushed the boundaries of what was possible, developing new techniques and uploading new software to the spacecraft to cope with the extreme conditions. On August 25, 1989, 12 years after launch, Voyager 2 arrived at Neptune. It was the grand finale of the Grand Tour, the last planetary encounter that Voyager would ever make. And Neptune did not disappoint. After the visual blandness of Uranus, many scientists feared that Neptune would be similarly featureless. After all, Neptune is even farther from the Sun, receiving even less energy to drive atmospheric circulation. If Uranus was bland, surely Neptune would be even blander. They could not have been more wrong. Neptune turned out to be one of the most dynamic, most visually striking, most meteorologically active planets in the solar system. The first thing that struck scientists as the images came in was the deep, vivid blue color of Neptune, a richer, more intense blue than Uranus's pale blue-green. Like Uranus, Neptune's blue color is caused primarily by methane in the atmosphere absorbing red light. But Neptune's blue is deeper and more saturated, which suggests that there is some additional unknown compound in Neptune's atmosphere that contributes to the color. To this day, the exact identity of this compound remains unknown, but the real showstopper was the weather. Neptune's atmosphere was alive with storms, clouds, and wind patterns that rivaled Jupiter's in their drama, if not in their scale. The most prominent feature was a massive, dark storm system in the southern hemisphere that the scientists named the Great Dark Spot, a deliberate echo of Jupiter's Great Red Spot. The Great Dark Spot was roughly the size of Earth, and it was surrounded by bright cirrus-like clouds of methane ice crystals, similar to the high-altitude clouds that form around the edges of hurricanes on Earth. These bright companion clouds changed shape and position rapidly, sometimes within just a few hours, giving the storm a dynamic, living appearance. And the winds. The winds on Neptune are the fastest of any planet in the solar system. At the latitude of the Great Dark Spot, wind speeds reached an astonishing 2,100 kilometers per hour. That is more than 6 times the speed of the strongest hurricanes on Earth. That is faster than the speed of sound in Neptune's atmosphere. These are supersonic winds on a planetary scale. And here is what makes this truly mind-bending. Neptune receives less than 1/1000th of the solar energy that Earth receives. There is almost no energy coming from the Sun to drive atmospheric circulation. And yet, Neptune has the fastest winds in the solar system. How is this possible? The answer lies in Neptune's internal heat. Unlike Uranus, Neptune radiates a substantial amount of excess internal heat, about 2.6 times more energy than it receives from the Sun. This internal heat, left over from Neptune's formation 4.5 billion years ago, rises through the atmosphere, driving powerful convection currents that generate the extreme winds. Why Neptune still has so much internal heat while Uranus has almost none remains one of the great puzzles of planetary science. The two planets are very similar in size and composition. They are often grouped together as ice giants to distinguish them from the larger gas giants Jupiter and Saturn. And yet, in terms of internal heat and atmospheric dynamics, they could not be more different. This difference may hold clues to their different formation histories or internal structures, but we do not yet have enough data to solve the puzzle. A future orbiter mission to either or both ice giants is desperately needed. There is a fascinating postscript to the Great Dark Spot story. When the Hubble Space Telescope turned its gaze on Neptune in 1994, just 5 years after Voyager's flyby, the Great Dark Spot had vanished. It was gone. A storm the size of Earth had simply disappeared. But a new dark spot had appeared in Neptune's northern hemisphere. Neptune's great storms, unlike Jupiter's Great Red Spot, which has persisted for centuries, are apparently transient features, forming and dissipating on timescales of years. This tells us something important about the differences between the atmospheres of the two planets, but exactly what it tells us is still being worked out. Voyager 2 also discovered that Neptune has a ring system, confirming hints from Earth-based observations. Neptune's rings are faint and tenuous, similar to the rings of Jupiter and Uranus, but they have a unique feature: ring arcs. Before Voyager's arrival, Earth-based observations had detected what appeared to be partial rings, or arcs, around Neptune, segments of rings that did not extend all the way around the planet. This was deeply puzzling, because the dynamics of orbital mechanics should cause ring material to spread out evenly around the planet fairly quickly. Voyager confirmed the existence of these arcs, which are concentrated clumps of material within an otherwise faint, continuous ring called the Adams ring. The arcs are thought to be maintained by the gravitational influence of a small moon called Galatea, which is in an orbital resonance with the ring particles, confining them into discrete clumps. The rings are named after French astronomers who contributed to the discovery and understanding of Neptune, Adams, Leverrier, Gala, and Arago. But once again, as at Jupiter and Saturn, it was a moon that provided the most dramatic and unexpected discoveries. Neptune's largest moon, Triton, turned out to be one of the most remarkable worlds in the entire solar system. Triton is unique in many ways. It is the only large moon in the solar system that orbits its planet in a retrograde direction, meaning it orbits opposite to the direction of Neptune's rotation. Every other large moon in the solar system orbits its planet in the same direction that the planet rotates, which is the natural consequence of forming from the same disk of material that the planet formed from. Triton's retrograde orbit means that it did not form around Neptune, it was captured. Triton is a refugee, a wanderer that originated in the Kuiper Belt, the vast ring of icy bodies beyond Neptune that is the home of Pluto, and was gravitationally captured by Neptune at some point in the distant past. Triton is, in essence, Pluto's cousin, a Kuiper Belt object that happened to wander too close to a giant planet and got trapped. The capture of Triton would have been a catastrophic event. When an object is gravitationally captured by a planet, it initially enters a highly elliptical orbit. As it orbits, tidal interactions with the planet dissipate orbital energy as heat, gradually circularizing the orbit. In Triton's case, this process generated enormous amounts of tidal heating, potentially melting the moon's interior completely. Any other moons that Neptune had before Triton's arrival would have had their orbits severely disrupted or would have been ejected entirely. Triton essentially wiped out Neptune's original moon system and replaced it. Today, Triton orbits Neptune in a nearly perfect circle, but its retrograde orbit means that tidal interactions are slowly stealing its orbital energy, causing it to spiral inward toward Neptune. Eventually, in roughly 3.6 billion years, Triton will cross Neptune's Roche limit, the distance within which the planet's tidal forces will tear it apart, and it will be destroyed, potentially forming a spectacular ring system around Neptune that could rival Saturn's. But that is a long time from now. Voyager 2 passed within 40,000 kilometers of Triton's surface, giving us our only close-up look at this extraordinary world. The surface temperature was measured at -235 degrees Celsius, making Triton one of the coldest objects ever measured in the solar system. The surface is covered in nitrogen ice, with traces of methane and carbon monoxide ice. Large portions of the surface display a peculiar texture that scientists called cantaloupe terrain, because it resembles the skin of a cantaloupe melon with a pattern of roughly circular depressions covering the surface. This terrain is unique to Triton and is thought to be formed by diaparism, the rising of less dense material through a denser surrounding material, similar to the way lava lamps work. But the most astonishing discovery on Triton was the geysers. Voyager 2 observed dark plumes of material erupting from Triton's surface, rising to heights of about 8 kilometers before being blown horizontally by winds in Triton's thin nitrogen atmosphere, leaving dark streaks on the surface downwind. These geysers are thought to be powered by a greenhouse effect in the transparent nitrogen ice. Sunlight penetrates the ice, warms the darker material beneath it, vaporizing nitrogen gas which builds up pressure until it erupts through the ice in a geyser-like explosion. This is active geology on a world where the temperature is only 38 degrees above absolute zero. It is a reminder that even in the coldest, most remote corners of the solar system, there is activity, there is dynamism, there is change. Triton may also have a subsurface ocean of liquid water, like Europa and Enceladus, maintained by the residual heat from its capture and by ongoing radioactive decay in its rocky core. If so, it would be yet another potential habitat for extraterrestrial life, hidden beneath an icy surface at the very edge of the solar system. Voyager 2 also discovered 6 previously unknown moons of Neptune and made detailed measurements of the planet's magnetic field, which, like Uranus's, is highly tilted and offset from the planet's center, reinforcing the idea that the ice giants generate their magnetic fields in a different way from the gas giants. And then, its grand tour complete, having visited all 4 giant planets and their retinues of moons, rings, and magnetic fields, Voyager 2 followed its twin into the void, heading southward out of the ecliptic plane toward interstellar space. The planetary encounters were over, but the most iconic moment of the entire Voyager mission was yet to come. It was February 14th, 1990, Valentine's Day. Voyager 1 was about 6 billion kilometers from Earth, farther than any spacecraft had ever been at the time. Its cameras had been shut off after the Saturn encounter in 1980 to conserve power. But one man believed that there was one more picture Voyager needed to take. His name was Carl Sagan. Sagan was an astronomer, a planetary scientist, a science communicator, and a dreamer. He had been involved with the Voyager program from the beginning. He was the driving force behind the Golden Record, the gold-plated copper disc attached to each Voyager spacecraft containing sounds, music, and images from Earth. And now he had an idea. He wanted Voyager 1 to turn its camera around, back toward the inner solar system and take one last picture. A picture of Earth. Many people at NASA were opposed. The picture would have no scientific value, they argued. Earth would appear as nothing more than a tiny, unresolvable point of light. And there was a risk that pointing the camera in the general direction of the sun could damage it, ending any possibility of future camera use. But Sagan was persuasive, and he had allies. He lobbied NASA relentlessly, and finally, NASA agreed. On February 14, 1990, Voyager 1 turned its camera back toward the sun and took a series of 60 frames, creating a mosaic of the inner solar system, a family portrait of the planets. In one of those frames, there was a tiny, almost invisible speck of light caught in a scattered ray of sunlight. That speck was Earth. It occupied less than a single pixel of the image. It was a pale, blue dot, barely distinguishable from the background noise. Carl Sagan looked at that image and wrote what is, in my opinion, the most profound and beautiful passage ever written by a human being. I want to share it with you now, because it captures something essential about what the Voyager mission means, not just for science, but for all of us. Sagan wrote, "Look again at that dot. That is here. That is home. That is us. On it, everyone you love, everyone you know, everyone you ever heard of, every human being who ever was, lived out their lives. The aggregate of our joy and suffering, thousands of confident religions, ideologies, and economic doctrines, every hunter and forager, every hero and coward, every creator and destroyer of civilization, every king and peasant, every young couple in love, every mother and father, hopeful child, inventor and explorer, every teacher of morals, every corrupt politician, every superstar, every supreme leader, every saint and sinner in the history of our species lived there, on a mote of dust suspended in a sunbeam." He continued, "The Earth is a very small stage in a vast cosmic arena. Think of the rivers of blood spilled by all those generals and emperors so that, in glory and triumph, they could become the momentary masters of a fraction of a dot. Think of the endless cruelties visited by the inhabitants of one corner of this pixel on the scarcely distinguishable inhabitants of some other corner. How frequent their misunderstandings. How eager they are to kill one another. How fervent their hatreds. Our posturings, our imagined self-importance, the delusion that we have some privileged position in the universe, are challenged by this point of pale light. Our planet is a lonely speck in the great enveloping cosmic dark. In our obscurity, in all this vastness, there is no hint that help will come from elsewhere to save us from ourselves. And then, the most beautiful part of all. It has been said that astronomy is a humbling and character-building experience. There is perhaps no better demonstration of the folly of human conceits than this distant image of our tiny world. To me, it underscores our responsibility to deal more kindly with one another, and to preserve and cherish the pale blue dot, the only home we have ever known. After the pale blue dot image was taken, Voyager 1's cameras were turned off permanently. There was no reason to keep them on. There would be no more planets to photograph, no more moons to image. The cameras would only drain precious power from the RTGs, and so the last image ever taken by Voyager, the last thing it ever saw, was its own home, the planet Earth, a tiny point of light in the vastness of space. I cannot think of a more fitting final photograph. The pale blue dot became one of the most famous and iconic images in the history of photography. It has been reproduced billions of times. It has inspired countless people to pursue science, to care about the environment, to look at the world with a sense of perspective and humility. It reminds us that all of our wars, all of our politics, all of our triumphs and tragedies take place on a tiny speck of rock in an indifferent cosmos. And it reminds us that we are all in this together, all of us, every human being on Earth, sharing this one fragile world. Now, let us talk about what may be the most beautiful and hopeful object ever created by humans: the Voyager Golden Record. Attached to the side of each Voyager spacecraft is a 12-inch gold-plated copper phonograph record enclosed in a protective aluminum jacket. On the cover of the jacket are instructions, written in symbolic language that any sufficiently advanced civilization should be able to decode, explaining how to play the record. There is a diagram of the record and the stylus needed to play it. There is a diagram showing the correct speed of rotation. There is a diagram showing how to convert the encoded signals into images. And there is a map, a pulsar map, showing the location of our sun relative to 14 pulsars, rapidly rotating neutron stars that emit radio pulses at precise known frequencies. By measuring the frequencies of these pulsars and comparing them to the frequencies indicated on the map, an alien civilization could triangulate the location of our sun and determine when the record was made, since pulsar frequencies change predictably over time. It is, in effect, a return address and a timestamp written in the universal language of physics. But the instructions on the cover are just the beginning. What is on the record itself is a time capsule of human civilization, a carefully curated collection of sounds, music, images, and greetings that was intended to represent the best of what humanity has to offer. The record begins with a series of greetings in 55 different languages, starting with Sumerian, one of the oldest known human languages, and continuing through a diverse sampling of modern languages from around the world. There are greetings in English, in Mandarin, in Hindi, in Spanish, in Arabic, in French, in Russian, in Japanese, in Urdu, in Bengali, and dozens more. Each greeting is different. Some are formal, some are casual, some are poetic. In English, the greeting is simply, "Hello from the children of planet Earth." In Mandarin, it says, "Hope everyone is well. We are thinking about you all. Please come here to visit when you have time." In Zulu, it says, "We greet you, great ones. We wish you longevity." Each greeting is a tiny window into a different culture, a different way of thinking about the universe and our place in it. After the greetings come the sounds of Earth. This section is a sonic portrait of our planet, beginning with the sounds of nature: wind, thunder, surf, the calls of birds and whales and elephants, the chirping of crickets, the howling of wolves. Then come the sounds of human life: footsteps, heartbeats, laughter, the cry of a baby. Then the sounds of human technology: a horse-drawn carriage, a train, a jet aircraft, a Saturn V rocket launch, and then, in a touch that I find incredibly moving, the sound of a human kiss and the sound of a mother saying to her baby, "Hello?" Then comes the music. 90 minutes of music from around the world, selected by a committee led by Carl Sagan and the creative director Anne Druyan. The selection is eclectic, beautiful, and deeply thoughtful. There is the first movement of Bach's Brandenburg Concerto No. 2, performed by the Munich Bach Orchestra. There's the first movement of Beethoven's Fifth Symphony. There is Mozart, there is Stravinsky, there is a Navajo night chant. There is a Georgian choir singing a traditional song. There is a Japanese shakuhachi piece called Tsuru no Sugimori, or Crane's Nest. There is an Indian raga performed by the legendary Sir Sri Kesar Bai Kerkar. There is Indonesian gamelan music. There is Peruvian panpipes. There is a Pygmy Girl's initiation song. There is Chuck Berry's Johnny B. Good, a rock and roll song that some committee members worried was too adolescent for such a solemn purpose, to which Carl Sagan is said to have replied that the teenage years are an important period in any civilization's development. There are 27 musical pieces in total, drawn from cultures and traditions spanning the entire globe and thousands of years of human history. Together, they form a portrait of human musical expression in all its diversity and beauty. And then there are the images. 116 images, encoded in analog form on the record, showing aspects of life on Earth. There is a diagram of our solar system. There's a photograph of the sun. There are images of the planets. There is a diagram of the structure of DNA. There is a drawing showing the anatomy of the human body. There are photographs of people from different cultures, different ages, different walks of life. There are images of landscapes, mountains, deserts, oceans, forests. There are images of animals, insects, fish, birds. There are images of human technology, a library, a highway, a telescope. There are images of food, a grape, a fish, a dinner scene. There are mathematical definitions, a circle, a triangle, the concept of diameter. The Golden Record is not just a collection of data, it is a love letter to the universe from the human race. It says, in effect, this is who we are, this is our world, this is what we have created, this is what we love. It includes no images of war, no depictions of violence, no references to our darker impulses. Some have criticized this as dishonest, as presenting a sanitized version of humanity. But I think the Golden Record's creators made a conscious and beautiful choice. When you send a message to a stranger, you put your best foot forward. You show them the best of what you are. You show them what you aspire to be. The Golden Record is not a documentary of human civilization. It is a declaration of our highest values, our deepest aspirations, our most beautiful creations. It is the version of humanity that we wish we could be all the time, and perhaps that is the most honest thing of all. There is one more detail about the Golden Record that I find incredibly moving, and it involves a love story. Anne Druyan, the creative director of the Golden Record, was responsible for much of the content selection. During the process of creating the record, she and Carl Sagan, who had known each other for some time, fell deeply in love. On June 1, 1977, just 2 months before the launch of Voyager 2, they became engaged. Druyan was overwhelmed with emotion, and she had an idea. She went to a laboratory and had her brainwaves recorded using an EEG machine, while she meditated on a series of topics. The history of the Earth, the history of life, the development of civilization, and at the end, the experience of being newly in love. Those brainwaves were compressed and encoded on the Golden Record, so somewhere on that disk, traveling through interstellar space at 17 kilometers per second, is the electrical pattern of a human brain experiencing the wonder of new love. Whether any alien civilization could ever decode those brainwaves and understand them is irrelevant. The beauty of the gesture is what matters. Human love, encoded in gold, flying through the void between the stars, forever. The Golden Record was designed to last 1 billion years in the vacuum of space. The metal will not corrode. The engravings will not fade. Long after the Voyager spacecraft themselves have ceased to function, long after their RTGs have decayed to inert metal, long after their antennas have stopped transmitting and their instruments have stopped measuring, the Golden Record will endure. It will drift silently through the galaxy, a message in a bottle in the cosmic ocean, waiting to be found. It may never be found. The chances are, in fact, extremely small. Space is unimaginably vast, and even 100,000 years from now, the Voyagers will still be in the relative neighborhood of our solar system, far from any other star. But the Golden Record is not really about the probability of alien contact. It is about us. It is about our need to reach out, to say, "We were here," to cast our voice into the void and hope that someone, somewhere, someday might hear it. And with the golden record secured to its side and its cameras now dark, Voyager continued outward into the unknown. The years passed. The decades passed. Through the 1990s, through the 2000s, through the 2010s, Voyager 1 and Voyager 2 continued their silent journey outward, each second carrying them farther from the sun, farther from Earth, farther from everything they had ever known. The sun grew smaller behind them. The radio signals from Earth grew fainter. The power from their RTGs slowly, inexorably declined. One by one, instruments were turned off to save power. Heaters were turned off, and instruments designed to operate at room temperature somehow continued to function at temperatures far below their design specifications, a testament to the over-engineering and robust construction that characterized the Voyager program. But the Voyagers were not just drifting passively. They were still doing science, still making measurements, still sending data back to Earth. And the science they were doing was unlike anything that had been done before, because they were approaching a boundary that no human-made object had ever reached, the edge of the heliosphere. To understand what the heliosphere is, you need to understand the solar wind. The sun does not just emit light, it also emits a constant stream of charged particles, mainly protons and electrons, flowing outward in all directions at speeds of 300 to 800 kilometers per second. This stream of particles is called the solar wind. The solar wind fills an enormous volume of space around the sun, creating a bubble called the heliosphere. Inside the heliosphere, the dominant influence is the sun. The magnetic field is the sun's magnetic field, carried outward by the solar wind. The charged particles are mostly solar particles. Outside the heliosphere, in interstellar space, the dominant influence is the galaxy. The magnetic field is the interstellar magnetic field. The charged particles are galactic cosmic rays, high-energy particles produced by distant supernovae and other energetic events throughout the Milky Way. The boundary between the heliosphere and interstellar space is not a sharp line. It is a gradual transition with several distinct layers. The first layer that Voyager encountered was the termination shock. This is the boundary where the solar wind, which has been flowing outward at supersonic speeds, slams into the resistance of the interstellar medium and abruptly slows down to subsonic speeds. Think of it like a garden hose pointed at a swimming pool. The water shoots out of the hose at high speed, but when it hits the pool water, it abruptly decelerates. The termination shock is where the solar wind decelerates. Voyager 1 crossed the termination shock in December 2004, at a distance of about 94 astronomical units from the Sun. An astronomical unit is the average distance from the Earth to the Sun, about 150 million kilometers. So Voyager 1 was 94 times farther from the Sun than Earth, about 14 billion kilometers. Voyager 2 crossed the termination shock in August 2007, at a distance of about 84 astronomical units. The fact that the two spacecraft crossed the termination shock at different distances from the Sun tells us that the heliosphere is not a perfect sphere. It is asymmetric, pushed in on one side and bulging out on the other, shaped by the interaction between the solar wind and the interstellar medium. Beyond the termination shock lies the heliosheath, a turbulent region where the slowed-down solar wind is compressed and heated. This is, to use a metaphor, the war zone between the Sun and the galaxy. The solar wind, now sluggish and turbulent, pushes outward. The interstellar medium pushes inward. The two forces clash, creating a region of extreme turbulence and complexity. Voyager's instruments measured a chaotic magnetic field in the heliosheath, with abrupt changes in direction and strength. They detected unexpected features, including what scientists called a magnetic highway, a region where the magnetic field lines were smooth and orderly, allowing charged particles to flow in and out easily, even though the spacecraft was still technically inside the heliosphere. The heliosheath turned out to be far more complex and interesting than anyone had expected. And then, finally, there was the heliopause, the ultimate boundary, the outer edge of the heliosphere, where the sun's influence ends and interstellar space begins. This was the line that everyone had been waiting for Voyager to cross. This was the moment that would mark humanity's entry into interstellar space. The problem was, nobody knew exactly where the heliopause was, and nobody was entirely sure how to tell when Voyager had crossed it. The transition was expected to be subtle, not like crossing a river or climbing a wall, but more like gradually moving from one region of fog into another. The key indicators would be changes in the density and composition of the charged particles around the spacecraft. Inside the heliosphere, most charged particles are solar wind particles. Outside the heliosphere, most charged particles are galactic cosmic rays. At the heliopause, there should be a dramatic drop in solar particles, and a corresponding dramatic increase in galactic cosmic rays. For Voyager 1, detecting this transition was complicated by the fact that its plasma science instrument, the instrument specifically designed to measure the density and speed of charged particles, had stopped working all the way back in 1980 during the Saturn encounter. Without this instrument, scientists had to rely on indirect measurements, using the cosmic ray detector and the magnetometer to infer what was happening to the plasma around the spacecraft. This was like trying to determine the weather by looking out a frosted window. You can see general changes, but the details are fuzzy. Voyager 1 began to see tantalizing signs that it was approaching the heliopause in mid-2012. In July and August, the cosmic ray detector registered a dramatic increase in galactic cosmic rays and a corresponding decrease in solar energetic particles. This was exactly what would be expected at the heliopause. But then, puzzlingly, the magnetic field did not change direction. Scientists had expected that the interstellar magnetic field would have a different orientation from the heliospheric magnetic field, and that Voyager would measure a sharp change in direction at the heliopause. No such change was observed. This led to months of debate among scientists about whether Voyager 1 had actually crossed the boundary or was in some new, unexpected transition region. The debate was eventually resolved in an unexpected way. In April 2013, a coronal mass ejection from the Sun, a massive burst of solar particles, reached Voyager 1's location. When it arrived, it caused the plasma around Voyager to vibrate, like a bell being struck. Voyager 1's plasma wave instrument, which was still functioning, detected these vibrations and measured their frequency. The frequency of plasma oscillations depends on the density of the plasma, and the density that Voyager measured was far higher than anything found inside the heliosphere. It was the density of interstellar plasma. Working backward from this measurement, scientists were able to determine that Voyager 1 had crossed the heliopause on approximately August 25, 2012. It was a historic moment. For the first time in the 4.5 billion year history of our solar system, an object created by intelligent life on one of its planets had left the Sun's domain and entered interstellar space. Voyager 1 was now an interstellar spacecraft. The news made headlines around the world. But in truth, the moment itself had occurred more than a year before it was confirmed, and Voyager itself had no idea. It just kept flying, as it always had, sending back its data, oblivious to the significance of what it had done. Voyager 2 crossed the heliopause on November 5, 2018, at a distance of about 119 astronomical units from the Sun. And here, Voyager 2 had a crucial advantage over its twin. Its plasma science instrument was still working. This meant that Voyager 2 could directly measure the density, temperature, and speed of the plasma around it as it crossed the boundary. The data confirmed the crossing unambiguously. As Voyager 2 passed through the heliopause, the density of solar wind particles dropped to near zero, and the density of interstellar plasma jumped by a factor of 20. The temperature of the plasma changed. The speed of the particles changed. It was a clear, definitive crossing. Both Voyagers were now in interstellar space. What have the Voyagers found in interstellar space? The answer is both confirmatory and surprising. First, the confirmatory. Galactic cosmic ray intensity did increase dramatically, as expected. These cosmic rays, high-energy particles produced by supernovae and other energetic events throughout the galaxy, are largely blocked from the inner solar system by the heliosphere. Outside the heliosphere, Voyager is fully exposed to the galactic cosmic ray flux. This is important not just for science, but for any future crewed missions beyond the solar system. Astronauts traveling through interstellar space would face a constant bombardment of cosmic rays, requiring heavy shielding or some other form of protection. Now, the surprising. The interstellar magnetic field turned out to be oriented in roughly the same direction as the magnetic field in the outer Helios heath. Scientists had expected a significant change in direction at the heliopause. The fact that the direction did not change much suggests that the interstellar magnetic field and the heliospheric magnetic field are more closely aligned than previously thought, or that there is some process at the heliopause that causes the fields to align. This is still being studied and debated. The density of the interstellar medium has also produced surprises. Voyager 1 has detected several regions of increased plasma density as it moves through interstellar space. These density enhancements are not uniform. They come in patches and waves, suggesting that the interstellar medium has structure and texture, that it is not the smooth, uniform sea of gas that simple models had predicted. NASA released audio representations of these plasma oscillations, converting the frequency of the vibrations into audible sound. The result is an eerie, otherworldly humming sound, the sound of interstellar space, the sound of the void between the stars. It is haunting and beautiful and deeply strange. The Voyagers have also detected what appears to be a slight increase in the density of the interstellar medium as they move farther from the Sun. This could mean that the local region of interstellar space through which our solar system is moving is denser on the outside than the models predicted. Or it could mean that the heliopause is pushing interstellar material outward, piling it up like a snowplow pushing snow. Either way, it is new data about a region of space that we have never been able to study directly before, and it is revising our understanding of the local interstellar environment. And then there is the shape of the heliosphere itself, which Voyager data is helping to constrain. For decades, the standard model of the heliosphere depicted it as having a comet-like shape, a blunt nose on the side facing the direction of the solar system's motion through the galaxy, and a long, tapering tail on the opposite side. But more recent analyses of Voyager data, combined with data from other spacecraft like IBEX, the Interstellar Boundary Explorer, have suggested that the heliosphere might not have a tail at all. Instead, it might be more nearly spherical, or perhaps shaped like a croissant. The debate is ongoing, and Voyager continues to provide crucial data points. Now, let us talk about where Voyager is today and what is happening to it. Because the story of Voyager in the 2020s is a story of heroic survival against impossible odds, and it includes some of the most heart-stopping moments in the entire history of space exploration. As of today, Voyager 1 is approximately 165 astronomical units from the Sun. That is about 24.7 billion kilometers. It is traveling at about 17 kilometers per second, or roughly 61,000 kilometers per hour. It is the farthest human-made object from Earth. Voyager 2 is approximately 138 astronomical units from the Sun, about 20.7 billion kilometers, traveling at about 15.4 kilometers per second. Both are in interstellar space, beyond the heliosphere, in the thin, cold medium between the stars. Communication with the Voyagers is maintained through NASA's Deep Space Network, or DSN, a system of 3 large radio antenna complexes spaced roughly equally around the Earth, in Goldstone, California, in Madrid, Spain, and in Canberra, Australia. This spacing ensures that at least one complex can communicate with any spacecraft at any time, regardless of the Earth's rotation. The DSN uses enormous dish antennas, the largest of which are 70 meters in diameter, to both send commands to and receive data from the Voyagers. The challenges of communicating with Voyager at its current distance are almost beyond comprehension. The radio signal that Voyager 1 transmits has a power of about 23 watts. By the time that signal reaches Earth, after traveling for more than 22 hours across 24 billion kilometers of space, it has spread out so much that the power received by the DSN antenna is about 10 to the power of minus 16 watts. That is 1/10 of a billionth of a millionth of a watt. It is 20 billion times weaker than the power of a digital watch battery. And yet the DSN can detect it, decode it, and extract meaningful scientific data from it. This is achieved through a combination of enormous antenna dishes, ultra-sensitive cryogenically cooled receivers, and sophisticated signal processing algorithms. It is one of the most remarkable feats of telecommunications engineering ever accomplished. The power situation on the Voyagers is the single greatest constraint on the mission's future. The RTGs on each spacecraft originally produced about 470 watts of electrical power, but plutonium-238 has a half-life of 87.7 years, which means that every 87.7 years, half of the plutonium has decayed and the power output has dropped correspondingly. After 46 years, the RTGs on each spacecraft produce approximately 220 watts, less than half their original output. This is not enough to power all of the spacecraft's systems simultaneously, so NASA has been systematically reducing power consumption by turning off instruments and heaters. The heating issue is particularly critical. Space is cold, but Voyager's electronics and fuel lines need to be kept above certain minimum temperatures to function. For decades, the RTGs provided enough power to run small electrical heaters throughout the spacecraft. But as the power declined, these heaters have been turned off one by one. The spacecraft's components are now operating at temperatures far below their designed minimums. The fact that they continue to function at all is a tribute to the quality of the engineering and a fair amount of luck. But this cannot continue indefinitely. At some point, probably within the next few years, the power will be insufficient to run even a single scientific instrument. And shortly after that, the power will be insufficient to maintain the spacecraft's basic communication systems. When that happens, Voyager will go silent. But before that final silence comes, there were 2 recent incidents that nearly ended the mission prematurely, and the stories of how NASA's engineers saved Voyager are among the most incredible tales of problem-solving in the history of technology. The first incident occurred in late 2023 and involved Voyager 1. In November of that year, Voyager 1 began sending garbled, nonsensical data back to Earth instead of the expected engineering and science telemetry. The spacecraft was alive and functioning and could receive commands, but the data it sent back was meaningless. Something had gone wrong with its Flight Data System, or FDS, one of the three onboard computers. Specifically, the computer responsible for packaging data before it is transmitted to Earth. Now, consider the challenges that the engineers faced in diagnosing and fixing this problem. The FDS computer uses technology from the mid-1970s. Its memory is measured in kilobytes, not gigabytes. There are no spare parts. There is no way to physically access the spacecraft. It is 24 billion kilometers away. Every command sent from Earth takes more than 22 hours to arrive. Every response from the spacecraft takes more than 22 hours to come back. A single round-trip communication takes nearly 2 full days, and the engineers working on the problem, many of whom were not born when Voyager was launched, had to pore through documentation written decades ago, some of it on paper, some of it on obsolete computer formats, to understand the arcane workings of this ancient computer system. After weeks of analysis, the team determined that the problem was a corrupted section of memory in the FDS computer. A small chip had gone bad, probably due to radiation damage or simple age, and the data stored in that chip was corrupted. Unfortunately, this chip happened to contain a critical portion of the code that the FDS uses to format telemetry data. Without this code, the FDS could not produce coherent data packets, and everything it sent was garbled. The solution was ingenious but risky. The engineers decided to relocate the corrupted code to a different, functioning section of the FDS memory. But the FDS memory was almost completely full. There was no single block of free memory large enough to hold the entire affected code section. So the team had to split the code into several smaller pieces and scatter them across different locations in the computer's memory, with instructions telling the computer where to find each piece. This is a technique well known in computer science, but performing it on a 46-year-old computer 24 billion kilometers away, with a 2-day round-trip communication delay, using documentation from the 1970s, on a spacecraft with no backup and no way to undo a mistake, was something else entirely. The process took months. Each step had to be planned meticulously, tested extensively on simulators, and then executed with excruciating patience, sending a command, waiting 22 hours for it to arrive, waiting another 22 hours for the response, analyzing the response, and then deciding on the next step. There could be no mistakes. A single wrong command could have crashed the FDS computer beyond recovery, ending the mission. In April 2024, after months of painstaking work, the relocated code was successfully installed and activated. Voyager 1 began sending coherent data again. The mission was saved. The engineers who accomplished this feat, bridging a gap of nearly 5 decades of technology and 24 billion kilometers of distance, deserve to be remembered as some of the greatest problem solvers in the history of human engineering. They saved a piece of history with nothing but ingenuity, patience, and a willingness to dig into the depths of obsolete technology. The second incident occurred in July 2023 and involved Voyager 2. A routine command sequence was sent to Voyager 2, but due to an error, one of the commands inadvertently tilted the spacecraft's antenna 2 degrees away from Earth. 2 degrees does not sound like much, but at a distance of 20 billion kilometers, 2 degrees is enormous. It meant that Voyager 2's radio beam, normally aimed precisely at the DSN antennas on Earth, was now pointed into empty space. Communication was lost. For 2 terrifying weeks, the longest-running mission in the history of space exploration was silent. The engineers tried everything they could think of. They used the DSN's most powerful transmitter, boosted to maximum power, to send a shout command to Voyager 2, a simple instruction to reorient its antenna back toward Earth. But even the DSN's most powerful signal, spread out over 20 billion kilometers, was barely detectable. The question was whether Voyager 2's backup receiver, with its known flaw of not being able to automatically compensate for Doppler shift, could pick up the signal and act on it. Days passed, the command was sent repeatedly, and then, finally, Voyager 2 responded. It had received the command and reoriented its antenna. Communication was restored. The mission was saved once more, but consider how close it came. If Voyager 2 had not responded, there would have been nothing else to try. The spacecraft would have drifted on through interstellar space, its antenna pointed in the wrong direction, unable to hear Earth's calls, transmitting its data into the void. After 46 years and 20 billion kilometers, the mission would have been ended by a 2-degree pointing error. Space exploration, for all its grandeur and romance, often comes down to tiny details like this. These incidents highlight a broader truth about the Voyager mission. Voyager is not just a scientific achievement. It is an ongoing act of human will. Keeping these spacecraft alive and functioning, year after year, decade after decade, requires constant attention, constant ingenuity, and constant commitment from a shrinking team of dedicated engineers and scientists. Every year, as the power declines and the technology ages, the challenges grow greater. Every year, the team finds new ways to squeeze just a little more life out of these incredible machines. It is a relay race across generations, with each new team of engineers picking up where the last left off, maintaining the connection to two tiny machines that are farther away than anything humans have ever built. So, what happens next? What is the future of Voyager? The power from the RTGs will continue to decline. By the late 2020s or early 2030s, there will not be enough power to operate any scientific instrument. At that point, the Voyagers will become silent sentinels, still flying, still carrying their golden records, but no longer able to communicate with Earth or make any measurements. The exact date of the final shutdown is uncertain, as it depends on which instruments can continue to operate below their design temperatures, and how creatively the engineering team can manage the remaining power. But it will come. It is inevitable. When the last signal from Voyager arrives at Earth, it will be one of the most poignant moments in the history of exploration. For nearly half a century, these two spacecraft have been our emissaries to the outer solar system and beyond. They have shown us wonders we never imagined. They have changed our understanding of our cosmic neighborhood. They have inspired generations of scientists and engineers and dreamers. And when the last faint whisper of their radio signal fades into the cosmic static, a chapter of human history will close. But the Voyagers themselves will not stop. They will continue to fly, silently, through interstellar space, essentially forever. There is nothing out there to slow them down. There is no friction, no air resistance, no obstacles. Newton's first law of motion says that an object in motion stays in motion unless acted upon by an external force. In the near vacuum of interstellar space, the external forces on Voyager are negligible. The very faint gravitational pull of the Sun will slow the spacecraft slightly over time, but by this point, the Voyagers have achieved escape velocity from the solar system. They will never fall back. They will never return. They are gone forever. But gone is a relative term. The Voyagers may have left the heliosphere, but they have not left the solar system, not really. The Sun's gravitational influence extends far beyond the heliosphere, all the way out to the Oort cloud, a hypothetical spherical shell of icy bodies that is thought to surround the solar system at distances of 2,000 to 100,000 astronomical units from the Sun. The outer edge of the Oort cloud, at 100,000 astronomical units, is nearly 2 light-years from the Sun, almost halfway to the nearest star. The Oort cloud is thought to be the source of long-period comets, icy bodies that are occasionally perturbed by the gravity of passing stars and sent falling inward toward the sun, where they develop their characteristic tails as they are heated. Voyager 1, at its current speed of about 17 kilometers per second, will enter the inner reaches of the Oort cloud in roughly 300 years. It will take about 30,000 years to pass all the way through the Oort cloud and emerge on the other side. 30,000 years. When Voyager 1 finally exits the Oort cloud and can truly be said to have left the solar system entirely, the year will be approximately 32,000 AD. Human civilization will be 30,000 years older than it is today. Think about how much the world has changed in the last 300 years, since the age of horse-drawn carriages and sailing ships. Now multiply that by 100. That is the timescale we are talking about. Whatever humanity becomes in that time, wherever we go, whatever we achieve, Voyager will still be out there, drifting through the dark. In about 40,000 years, Voyager 1 will make its closest approach to a star called Gliese 445 in the constellation Camelopardalis. But closest approach is a relative term. Voyager 1 will pass within about 1.6 light-years of this star. That is about 9.5 trillion kilometers. It will not enter the star's planetary system if it even has one. It will not be captured by the star's gravity. It will simply drift past, a silent artifact from a distant civilization, and continue on its way. Voyager 2, heading in a different direction, will pass near the star Ross 248 in about 40,000 years, and near Sirius, the brightest star in Earth's sky, in about 296,000 years.